Hello, fam. This is our lesson for normal distributions. We have just covered standard deviation and z-scores. So everything in this unit that we are talking about, remember this is our really short unit where we're just going to do 4 lessons. And our 4 lessons are standard deviation, z-scores, normal distribution, and percentiles. I decided to group these ideas together because they're all based around this idea of standard deviation. Now, percentiles is more related to the normal distribution than anything else, but our first 3 are really based around this idea of standard deviation. So standard deviation is the I'm sorry, I'm trying to find the perfect definition. It measures the typical distance of the values from the mean. So we have a bunch of data values in a data set. We can describe that data set with an average or a mean. And then further, we can describe it with this idea of standard deviation, which tells you about how far away from the mean are the other data points or the other observations. We talked about how typically we want a small standard deviation. We want our data to be clustered around the mean. This would represent a small standard deviation. This would represent a larger standard deviation. If we want to make predictions or use a data set to make inferences, a standard deviation that's smaller is better because it makes our data more reliable, whereas for this data set, it may not be as reliable to make predictions with this data set because the data is so spread out. So standard deviation describes the typical distance the observations are from the mean. So then we went into z-scores and we talked about how we can take any observation in the data set and describe it by telling how far away from the mean it is in terms of standard deviations. Because standard deviations is a really important measure of spread. I mentioned how with standard deviation, most of your data will be within 1 standard deviation of the mean. So standardizing the scores or finding a z-scores allows us to do 2 things that are really important. Number 1, it allows us to see if an observation is unusual. So if we're within 1 standard deviation of the mean, then that observation is where most of the data is. If we're 2 standard deviations from the mean, we're starting to get an unusual observation, unusually high or unusually low. And if we're 3 or more standard deviations from the mean, that usually means we have an outlier. That observation is very unusual. So that's the first thing. We can use it to determine if our observations are unusual, and a lot of the time that's because we're doing some kind of comparing. Like we've looked at blood pressure in one of our examples, and so we want to know if a specific person's blood pressure is unusual, and I'm sure that you guys can understand that might be something really helpful to know. We can tell if it's unusual because we standardize the score, make it a z-score, and then that tells us where does this person's blood pressure fall within normal blood pressure. The other thing that z-scores allow us to do, which I personally think is very cool, my favorite thing about z-scores, is it allows us to compare 2 different distributions. So I can compare a chemistry score to a calculus score by standardizing, and I can compare and say, oh, well, this student did much better in calculus than they did in chemistry. The reason why that is important is because chemistry and calc are 2 different courses. Their difficulty levels are similar, but they're addressing different skills. And because of that, it makes it hard to compare. But if we standardize the score, it does allow us to compare a student's performance in each of the classes, even though they're different. So standard deviation tells us how far away on average are observations in our data set from the mean. And then a z-score allows us to describe an observation in terms of standard deviations. How many standard deviations is an observation from the mean? Because that allows us to make a lot of really important comparisons. So standard deviation, super important. Let's go back to my paper. Super important, tells you how far away on average observations are from the mean. And then z-scores, I think z-scores are very cool. They put your observation in terms of standard deviations. So now we're going to move into this idea of a normal distribution. So we're going from the idea of a standard deviation, the idea of a z-score, and now we're going to discuss the shape of a distribution. And it's a shape that is very important and very useful in statistics, and that is the normal distribution. So let me go to my blank notes and we will start filling this in. So I'm going to do just a little bit of highlighting for myself. I haven't done this much in your class yet, but I like to make my notes pretty. Okay, so we know from Unit 1 that data can be distributed many different ways. So our first histogram that we're seeing is left skewed, then we have a right skewed, this guy multimodal. He's kind of looking bimodal, but I think he's multimodal. This guy, he's interesting, he's unimodal, he has a slight skew. I would say maybe not, maybe he's roughly symmetric. He's a little bit harder to determine. But here we can see 4 different shapes that data or distribution can take on. Now, the only reason that I've chosen histograms to show you those shapes is because lots of the times histograms are the easiest way to see a shape. But remember, we can determine the shape from a dot plot, a stem plot, or a box plot. So data can be distributed in many different ways, but the most important distribution in AP statistics is the normal distribution or the normal curve. So the most important distribution, the most important shape in AP stats is the normal distribution. And I'm hoping that lots of you guys saw this last year in your Math 3 class. If you had me, then you for sure saw it last year in your Math 3. So here's a very good description of the normal curve. So data that tends to be around a, sorry, I'm just looking for my pencil. Central value, data that tends to be around a central value with no bias left or right, so that means no skew. I'm going to write skew above the word bias. Is said to be normally distributed. So now let's fill in some of these blanks that I didn't. So data that's around a central value with no skew looks bell-shaped. So that blank I left out is the word bell. The second blank that I left out is that we very rarely say something is normally distributed. We often have to say it's approximately normally distributed. Then right here, this histogram with the curve laid over it gives you a really great picture of a normal distribution. And this guy is approximately normal. He's not perfectly normal, he's approximately normal. So now we're going to get into the most important descriptions of the normal distribution, and this is where standard deviation comes in. So the description we're about to fill in with these bullet points is where we bring in the idea of standard deviation. So the normal distribution, and we typically try to capitalize the word normal. I often forget, but lots of textbooks, lots of problems, lots of support materials will capitalize that. So the normal distribution is bell-shaped. So notice I put this little bell here for you so that you could make the connection between this shape and this shape. It's symmetric and it's unimodal. All normal or approximately normal distributions are bell-shaped, symmetric, and unimodal. So if we go back up to this curve, then that allows you to see why we can say that this is only approximately normal, because look at these two bars right here. Those are not exactly the same height. So this is not exactly symmetric. It's approximately or roughly symmetric, which then makes it approximately normal. So that's why most of the time we don't say it is a normal distribution, we say it's approximately normal. It has a mean mu. So let me take out a different piece of paper to show you how you write mu. He's like a U, so a U with a tail, but he has like a tail on the front too. Notice how he kind of looks like an M. So this is called mu. So how I draw it is I'll start on the left, I'll come up, draw my U, give it a tail. So has a mean of mu. And a standard deviation of sigma. So sigma is just like a circle with a line on top. So circle, line. Circle, line. So don't confuse it with theta. That's theta. Sigma's more like this. So we describe the mean and the standard deviation of all normal distributions with the symbols mu and sigma. When you get a normal distribution, you usually have to name it, and you name it by writing capital N, parenthesis, mu, comma, sigma. So whenever we make a normal distribution, we have to go through and name it, and you name it like this, capital N, mu, sigma. And then you fill in what these values are. So now here comes the most important part about a normal distribution. This is the most interesting or useful thing about a normal distribution, and it is all based off of standard deviation. So you heard me say in previous lessons and at the beginning of this lesson that most of the data is within one standard deviation of the mean. Now we're going to formalize this. So if you have an approximately normal or normal distribution, 68% of the data will be within 1 sigma of the mean. Sorry, I'm just choosing the color that I want. I think I want this color. So 68% of the data, that is most of the data. That is a majority of the data. 68% will be within 1 standard deviation or 1 sigma of the mean. 95% of the data will be within 2 sigmas, and 99.7% of the data will be within 3 sigmas of the mean. That's why when I was saying a z-score allows us to describe if an observation is unusual. Well, if an observation is more than 3 sigmas away from the mean, it's very unusual because almost all of the data, 99.7% of the data, will be within 3 standard deviations. So our Babe Ruth example, where he was 5 standard deviations away, means he's definitely an outlier and he's super unusual. He's that 0.3% that is not within 3 standard deviations of the mean. His number of home runs represents less than 1% of all of the players. So I personally think that the normal distribution is really cool and z-scores are really cool because of this. Like, the idea that Babe Ruth would be 5 standard deviations away when almost all the other observations, like, it's basically impossible for Babe Ruth to hit that many home runs, and he did. I don't know. For some reason, that idea, analyzing that kind of data, is very interesting to me. So this idea here, where we write out 1 sigma, 2 sigma, 3 sigma, is called the empirical rule. This is called the empirical rule. That's just his name. We don't really got to worry over it. Sorry, I'm trying to find my purple pen. So this idea here is called the empirical rule. And we usually refer to it as the 68, 95, 99.7 rule. So we usually call it the 68-95-99.7% rule. Because this is true about every single normal curve. Every single normal curve or approximately normal curve. Within 1 standard deviation is 68, within 2 is 95, within 3 is 99.7. And I'm hoping at this point you can see why I've decided to put these 3 lessons together. Standard deviation, z-scores, and now this normal curve whose usefulness is based around standard deviations. So now I want to do a visual representation of this empirical rule. So I want to use the 68, 95, 99 rule. I want to give you a visual of that. So to draw a normal curve, we're going to draw our x-axis, and we're going to do the best that we can to make a normal curve. Mine are never awesome. My curve is pretty good, but I have a really hard time with the tails. So right in the center of your curve, we're going to put mu. Then to the right, you would describe this as 1 sigma, 2 sigma, 3 sigma. And notice that 3 sigma is it's very far to the right. It's very far to the right. Just fixing my curve up a little bit. Now to the left, we do -1 sigma, -2 sigma, -3 sigma. And they have to be negative because you're below the mean. You're below the mean. The name of this normal curve is capital N mu sigma. Remember, we're supposed to name them. So in terms of the distance, you decide. Like, it doesn't matter how far away you put these tick marks. The most important thing is that you put your mu in the middle, and then moving out, you know that this is 1 standard deviation away, 2 standard deviation away, 3 standard deviations away. Standard deviations below are negative, standard deviations above are positive. So what we just discussed is that if we put a boundary or a line at -1 sigma and 1 sigma, what is in between now represents 68% of the data, which should make sense because look at the curve. Most of the data is right here centered around the mean, because remember, all normal distributions are symmetric, unimodal, and centered or clustered around a central value. So if you look at the curve, most of the data is within these sigmas. So that's the 68. So now I'm going to draw another normal distribution. And it's the same. Mu is in the center, 1 sigma, 2 sigma, 3 sigma. -1 sigma, -2 sigma, -3 sigma. So this time I'm only going to label my 2 sigmas. And I'm going to draw my boundary value. And now I'm going to shade that guy in as soon as I spend 10 minutes deciding on a color. Am I the only person that does this? I swear. So this is 95% of the data. And then I'm sure you can see where we're going with the last one. Gonna have to draw kind of a baby distribution on this guy, because I'm running out of room. I'm probably moving a little bit faster than you guys, so if you need to pause, obviously you're gonna do that. Well, hopefully it's obvious. In all of these pens, I got 16 new pens. None of them are green. What is up with that? Okay, this may be the point where you want to pause to catch up to me. So, okay, there's probably a weird edit there because I ran out of space as usual. So hopefully we're both looking at the same three distributions. I had you draw out these distributions, for a couple of reasons. Number one, I wanted you to have the practice of drawing a normal curve because you have to do that quite frequently. Number two, I want you to see the empirical rule split out on its own, meaning I want you to see on its own graph what 68% looks like, what 95 looks like, and what 99.7 looks like. Because down here, they just put it all together. So these are like your cheat sheets for the empirical rule. So this first one is showing you on the same normal curve what we just separated out and did in three separate curves. It's showing you that this is 68%, this is 95%, this is 99.7. Down here, this is the same thing. Mu plus sigma is the same thing as saying 1 sigma. Mu plus 2 sigma is 2 sigma. Mu plus 3 sigma is 3 sigma. This will make a little bit more sense on the next page, and so will this. So what they've done here is they have taken this empirical rule and they have broken it down to determine how much data is within that 1 sigma section. So from U to 1 sigma is 34% of the data. And from 1 sigma to 2 sigma is 13.5% of the data. Hopefully that's making sense, because if the middle is 68, then that means if you split it in half, this is 34, this is 34. If this is 95%, and you know that the middle is 68, you can determine how much percent these have, which is 27, I think, and then you divide that in half. So this is taking each little sigma and telling us how much data is within that standard deviation. So here is it on its own, the empirical rule on its own. Here's on one graph, here it is on one graph. Here it is broken down by section. So now let's see how we use this. This is all of the application now. So notice this is our using the empirical rule section. Using the empirical rule. I tried to give you this little cheat sheet at the top of all of our pages because it is going to become very useful. So IQ is normally distributed with a mean of 100 and a standard deviation of 15. Label the normal curve. So the first thing that we have to do is name it. This is capital N, 10, just kidding, 100, comma, 15. That's its name. How do I know that? Because this is what we discussed right here. Now they want us to go down here and label these tick marks. So we know that the center is mu. The center is always mu. So this is 100. Okay, well, one standard deviation to the right is 15 IQ points. So this is 100 plus one standard deviation, or 115. Then to get the next one, I just add 15 again. So this tick mark is 130. And then this last tick mark, he's really hard to see, is 145. This is what they mean by label the normal curve. Okay, now we can go in the other direction. We do 100 minus the standard deviation, so 100 minus 15 is 85. Minus 15 is 70. minus 15 is 55. This number here is the same as mu minus 3 sigma, or 100 minus 3 times 15. That will give you 55. But instead of doing it as that equation, I prefer to just start at mu and minus, minus, minus. So just to label a little bit more so we're all clear, this center is mu. This is 1 sigma, 2 sigma, 3 sigma. Negative 1 sigma, negative 2 sigma, negative 3 sigma. So you can either start at the center and add, or you can do 100 plus 15. 100 plus 2 times 15. 100 plus 3 times 15. So I think maybe I'll write that here as well. This is mu plus 2 sigma, which would be 100 plus 2 times 15, which does give you 130. Okay, next up, the average temperature in August in Salt Lake City, Utah is 90 degrees with a standard deviation of 3 degrees. The temperatures follow a normal distribution. Label the normal curve. So this goes back to capital N, mu, sigma. We always have to name our normal curve. Then down at the bottom, we fill in our information. So the middle is always mu, so that's going to be 90. Then I go to the right first because that's easier for me. 90 plus 3 is 93, plus 3 is 96, plus 3 is 99. Now I go the other direction. 90 minus 3 is 87. 90 minus 3 is 87 minus 3 is 84. 87, just kidding, 84 minus 3 is 81. And now we get to answer some questions. So the first one is, what percent of the days, so what percent of the days are between 90 and 96? So I'm going to come over here to my curve, and I'm going to put a line at 90, and I'm going to put a line at 96. And I can see that that is made of these two sections. Well, using my cheat sheet up here, I know that this section is 34% and this section is 13.5%. So if I want to know how much is between these two values, I add those. So what percent of days are between 90 and 96? Well, 34% plus 13.5% gives me 47.5% of the days in August are between 90 and 96 degrees. I feel like that's extremely interesting that we can calculate that, because this is a normal curve. We can say with confidence that in August, 47.5% of the days are between 90 degrees and 96 degrees. How many days are between 90 and 96? Well, 47.5%. So now we need to calculate that. There's two ways to change this to a decimal. I'm going to show you both ways. So 47.5, the first way is to move the decimal 2 to the left. 1, 2. It is always 2. It is always 2. So now what that means is that this is 0.475. If you don't like to move the decimal, then you take 47.5 and you divide it by 100. Your calculator then will give you 0.475. Then we take the decimal, 0.475, and we multiply it by the number of days in August, which is 30. We plug that into our calculator, and that tells us that 14.25 days are between 90 and 96. Now, I know that we can't have 0.25 of a day, so I'm just going to leave it like that. But, I shouldn't say so, but I'm just going to leave it like that. They don't mark you wrong if you don't round up. They're okay with the fact that you write 14.25 because they want to know, do you have the understanding? They're not testing your math skills, they're testing your understanding. Okay, next up, a fire department in a rural county, that says count, in a rural county claims their response time is at most 15 minutes. At most 15 minutes. So that means it can be 10, 7, 13 and a half, 15, at most 15. The actual response times for the department are normally distributed with a mean of 22 minutes and a standard deviation of 7 minutes. According to the actual data, what percent of the times are 15 or less? Okay, so the actual data has a mean of 22 and a standard deviation of 7. So let's name this normal curve. And then let's fill in the bottom values. I'm not going to say it out loud because I'm hoping you're doing it with me, and then just checking once you have it filled in. Okay, mine's filled in. Might want to, well, you probably already saw it, so. Okay, so what percent of the times are 15 minutes or less? So here's 15 minutes. I like to label mine with a flag. This will become very, very important in the next unit, but I like to label my boundary. So we want to know what percent is this. Okay, well, I have my cheat sheet up here, So I'm going to say the percent, capital P, of response time. So I'm going to say X. X is response times. The percent of response times that are less than or equal to 15 is this first standard deviation, so that is 13.5, plus this next standard deviation, which is 2.35. And then you have this little smidgen right here that's less than 1%. It's almost 0. It's 0.15. So I'm going to label my curve. This one was 235. This one was 13.5. I have to add in that little smidgen because it says 15 or less, which means it's all the data to the left. So if we add all those together, we get that 16% of the response times are less than or equal to 15 minutes. So the fire department's claiming that most of their times, that their response times are at most 15. This says no, they're not. Only 16% of your response times are at most 15. So, liar. Okay, now there's one more thing to learn, and then the next page is all practice to make sure that we understand. So number 4, a distribution has 99.7% of its data between 42 and 156. Okay, so find the mean and the standard deviation. Step number 1 is to go and label those values. So I'm putting my tick marks down. 99.7 is 3 sigmas out. So 99.7 means 1, 2, 3 sigmas. So that means that on the right-hand side, this farthest tick is 156. And on the left-hand side, the smallest tick is 42. And they want us to use that information to figure out standard deviation and the mean. Okay, well, if we want to know the mean is the middle point between the number that is between 42 and 156. It is the number that is between 42 and 156. And I'm hoping that something is jiggling in your brain space to remind you, oh, we've done something like this before. Yes, we have. We have done something like this before. This actually has a formula that we can use. When we did median, what we did to find the median was add these two numbers and divide by 2. It's the same process here. If you want to know the number that's in the middle of these two, you add those two values, divide by 2. So if you want to know the median, or mu, you're going to take the lower bound that they give you and add the upper bound that they give you and divide it by 2. I know that from our experience with median. So underneath here, I can say mu is, my lower bound is 42. My upper bound is 156. Divide that by 2. Plug that into my calculator, and I get a mean of 99. So now I can place that right in the center. Now, I am sure that a lot of you guys can figure out how to find standard deviation now, because these, we have to add the same amount to get to 156. So I'm sure some of you could figure it out without a formula, but I am going to give you a formula. So the formula for calculating sigma is you take your upper bound and you subtract your lower bound. Then you divide by the number of sigmas between. You divide by the number of sigmas between. So sigma then is 156 subtract 42, or you could do 156 subtract 99, or you could do 99 subtract 42. You have a lot of options. You just have to take an upper bound, subtract a lower bound, and divide it by the number of sigmas between. So between 42 and 156, I just count the sections. So 1, 2, 3, 4, 5, 6 sigmas are between those. If you use this as your lower bound and upper bound, you would divide by 3. 1, 2, 3. You plug this into your calculator and you get 19. Then the last step that I do, especially if it's a problem like this, is I go through and verify that I got it right. And how I do that is I add 19. So 99 plus 19, I need my calculator. Oh, I almost fell off this chair. That would have been interesting. Is 118. And then 118 plus 19 is 137. So that means 137 plus 19 better be 156, and it is. It works the other way as well. 99 subtract 19 is 80. 80 subtract 19 is 61. 61 subtract 19 is 42. So now I can name this distribution. This is normally distributed with a mean of 99 and a sigma of 19. So this page is an excellent summary of what you can do with a normal curve. So now this third page is all practice. This third page is all practice. So I'm going to walk you through number 5 maybe. Suppose that the distribution of test scores is approximately normal and the middle 95% of scores are between 72 and 84. Calculate the percent of scores that are, okay, so step number 1, we got to draw our curve. Step number 2, we got to find the values. So over here, I'm going to draw my normal curve, mu in the middle, 1, 2, 3, 1, 2, 3, and they tell me that 95 so that's 2 sigmas out, is between 72 and 84. Well, I can't find any of these values. I can't answer any of the questions, sorry, unless I figure out what the other ticks are. I mean, I could answer letter B, but I should probably go through and find what these missing values are. So I'm going to do that. to the side. I'm not going to say what I'm doing though, because I'm hoping that you will also be trying to figure this out. So I'm going to find mu and sigma. Okay, I filled in my normal distribution. So if you need more time, you should pause, and now I'm gonna get started. So what percent of the scores are above 81? So I'm gonna go to the 81, I'm gonna plant a little flag. This is where X is 81. What is X? X equals the test score. What percent are above? So that's every single thing to the right. So using my cheat sheet, I'm going to come up here and I'm going to say, okay, that's 13.5 plus 2.35 plus 0.15. So that's going to be 16%. What percent are below 72? So I'm going to plant a flag. This is where X is 72. So I have to do everything below that. So that is my little smidgen percent, 0.15 plus 2.35. So 2.5% of the data is below 72. Okay, what interval contains 68% of the scores? Well, we know that that's between 1 sigma and -1 sigma. So this is 68%. Okay, well that aligns to 75 and 81. So what interval? A score of 75 to 81. If there are 38 students, how many scored between 78 and 81? Okay, 78 to 81. 78 to 81 is 34%. Is 34%. 78 to 81 is 34%. So 34%, you move the decimal to the right or divide by 100. So 1, 2, or 34 divided by 100, either give you 0.34. So we take 0.34, multiply it by the 38 students, and we get 12.92 students. Now, I know that we can't have 0.92 of a student, but I'm just going to leave it as that because I don't want to worry. Do I round down? Do I round up? I've shown that I know how to use the normal curve. So I am going to leave it as that. Okay, at this point, I think that you should pause the video. You should pause the video and try 6. Oh man, these are numbered wrong. 6, 7, and 8. You do 6, 7, and 8. Then you unpause and come back to watch the solutions. You unpause, come back. Uh-oh, family, before you pause, I forgot to name this distribution. That's a big deal. This is distribution 78,3. If you forgot to name yours, go back up and do it. Okay, pause. Come back and get your solutions. Okay, number 6. The mean lifetime of a computer laptop follows an approximately normal distribution with a mean of 28 months and a standard deviation of 9 months. Label the normal graph. Got it. N 28, 9. Got my values down at the bottom. Report how long the middle 68% of the laptops will last. That's going to be this section that I have marked, which is 19 to 37. How long will the middle 99.7% last? That is the shorter rectangle, which goes from 1 to 55. What percent is more than 37? I have that marked here. It's 16. Out of 500 laptops, how many will last more than 28 months? Well, 28 is the center of the data, which means that there's 50% above and 50% below. So 50% times 500 is 250 laptops. Or you would add 34, 13.5, 2.35, 0.15, and that would give you 50%. Number 7 is one of my favorite problems ever. Place these students on a normal graph at the appropriate locations. Abby is in the bottom 25%, so she's down here. Notice that I've colored in all that space. Kirk is in the top 16%, so Kirk is somewhere in this seafoam section. And 50% of the students are below Nick. That goes back to this problem up here where I wrote 50% above and below. That means Nick is right in the middle. Nick is the median. Or maybe not. Maybe, I don't think Nick has to be the median actually. So I'm going to erase that. Because 50% can be above him. Or sorry, 50% can be below him, but Nick could be in the 50% above, which means the median might be between Nick and the lower bound. If that makes no sense to you, just ignore and make sure that you know that Nick would be at the center of the data set. Then the last one, the scores on an AP chemistry exam are approximately normally distributed with mean 150 and a standard deviation of 15. What percent of the students who took the test scored between 180? That's 2.5. Notice that even though it didn't tell me, I have drawn, labeled, and named a normal curve, and I have shaded in the sections that I have added because, family, on these problems, you do not get full credit unless you show work. So even though the likelihood you're cheating off your neighbor is very small, especially in the actual exam, if you don't show work, you will not get full credit. So 2.5% scored above 180. What percent scored above 150? Well, 150 is the center. So that means 50%. How many scored less than 150? 50%, because that's the center. What percent of students scored between 120 and 165? 81.5. what percent of students scored between 105 and 135? 15.85%. On any of these answers, I could be wrong. So if you're sure you're right, you stick with what you have. It's class change, so sorry. But I'm pretty sure that these are right. I have written here that this is the median, but I think I need to think about that. Is that really the median? I think it is the median. I think 150 would be considered the median. But up here, I'm not 100% convinced that Nick is the median. Because Nick could be in the upper 50%. He's at the center, so I need to think about this one. But I'm pretty sure that this one, B and C, I'm pretty sure that 150 is the median. I'm going to think about that and then let you guys know when I see you in class probably what I decided. If I don't and you care, somebody remind me, because I'm sure I'm going to figure it out. I just might forget to tell you. Okay, so I'm feeling a little flustered because kids are waiting outside my room, but I want to make sure that I got through everything. So remember, when you see me in class next time, I'll answer any questions that you have from this lesson, and then you will work on your can you do in class. Please bless that you're actually doing that you're actually taking advantage of doing the lessons at home and the can you do's in class, because I really do think that it will benefit you. So if you're watching this in class right now, watch your lessons at home, ask your questions when you see me, and then work on your can you do's. Okay, love you, Mooey. Have a great rest of your day.